Welcome back. In this video, we're going to look at examples of finding area under polar curves. Let's get to it. All right, so here's our first example. We want to find the area of the region enclosed by r equals 3 plus sine theta. All right, so in order to find the area underneath a polar curve, which would be represented by this polar equation that we have right here, we need to know the formula for calculating area under polar curves. And the formula looks like this. The area is equal to 1/2 times the integral from alpha to beta, where both alpha and beta are angles of theta. And then inside the integral, we have r squared times d theta. All right, so as I said, the bounds of integration, alpha and beta, are values of theta. Those are the two angles for which the area we want to calculate lies between. And then for r is just equal to whatever your polar equation is equal to. R is equal to 3 plus sine theta, so we would replace r in this integral with 3 plus sine theta. All right, so the easiest part of these problems is replacing r with what it's equal to, but the more difficult part of these problems is determining the bounds of integration. What are going to be the two angles of theta that the area that we want to calculate lies between? And so in order to determine what those values of theta will be, I always recommend that you sketch a graph of your polar equation so that you can see the area that you're trying to calculate. All right, so in this case, we need to graph this polar equation 3 plus sine theta. Now, if you're not familiar with graphing polar equations, be sure to check out my videos on that topic. I have a lesson video and an examples video on graphing polar equations. But if you are familiar with graphing polar equations, we're going to go through this process pretty quickly. I'm going to make a quick sketch of this polar equation. This polar equation is in the form of a limacon, right? It's in the form of r equals some constant plus another constant times sine theta. In this case, our first constant is 3 and our second constant is 1, right? The form of a limacon is that r is equal to a plus or minus b times sine theta. Now you could also have cosine theta here, but in this case, we're working with sine. And so for our equation, a is equal to 3 and b is equal to 1. All right, so a is equal to 3 and b is equal to 1. Now in order to identify what type of limacon we're going to be working with here, we need to take a divided by b. And so in this case, a divided by b is equal to 3 divided by 1, and that is equal to 3. And so a divided by b is equal to 3, which is bigger than 2. It's greater than or equal to 2, which means that this limacon will be a convex limacon. All right, and so the basic shape of a convex limacon is basically a circle that is flattened on one end. So when you're working with the sine function, that will look something like this. All right, I exaggerated that flat end a little bit, but this is the general shape. It looks like a circle on top, and then below the polar axis, you're going to be flatter, and then you come back around. Okay, and so then this back end of the convex limacon, this is going to be located at a r value of a plus b. In this case, a is 3 and b is 1, so 3 plus 1 is 4. So the back end of our limacon along the angle of pi divided by 2 will be at the radius value of 4. So if we look at our polar graph here, each of these concentric circles I'm going to say is a unit of 1 for the radius. So if we count 1, 2, 3, 4, this fourth circle will represent a radius of 4. So I'll plot one point right there, and then the limacon is going to cross through the polar axis at the value of a on either side of the vertical axis. So our value of a is 3. So what we're going to do is count 1, 2, 3 right here. We'll have a point right there that our graph is going to cross through. And then on the other side, 1, 2, 3, we'll have a point right here. All right, so that's where our graph is also going to cross through. And then finally, this flat edge of our convex limacon, that's going to come out to a radius of the absolute value of a minus b. So a minus b in this case would be 3 minus 1, which is equal to 2. And the absolute value of 2 is 2. So the flatter edge of the convex limacon will come out to a radius of 1, 2, right there. So I'll draw that point. Okay, so now if we connect our points, that means that the graph of our polar equation will look something like this. Okay, you can see that our shape is more rounded on the top part and it's flatter towards the bottom. So that's how you graph our polar equation. And now that we've done that, we can see that the area that we want to calculate in this problem is this area right here, within this convex limacon. And so the question is, if we want to calculate this area, what two angles of theta does this area lie between? Well, remember, one full loop around the polar coordinate system is an angle of 2 pi. And as you can see, the area within this shape is contained around this whole coordinate system, right? Our polar curve that we're calculating the area underneath would start right here at this angle of 0 and make a full loop. And so we need to calculate the area underneath this curve all the way from 0 to 2 pi. So our two angles will be 0 and 2 pi. Our lower bound will be 0 and our upper bound will be 2 pi. So we will have that the area is equal to 1/2 times the integral from 0 to 2 pi of r squared, where r is 3 plus sine theta. So we will have 3 plus sine theta squared times d theta. Okay, so this definite integral represents the area enclosed by this polar curve. Now, if you wanted to, you could make use of symmetry here. Since this convex limacon is symmetric about the vertical axis, it's the same on the right side as it is on the left, right? If we change the bounds of integration to be from negative pi divided by 2 to positive pi divided by 2, that would calculate the area from this angle to this angle, which is only half of the shape. But if we doubled it by multiplying the definite integral by 2, that would account for the other side, since the shape is symmetric about the vertical axis. But that would just make things more difficult in this case. I would rather work with bounds of integration of 0 to 2 pi instead of negative pi divided by 2 to positive pi divided by 2. And so I'm going to leave our definite integral in this form. I'm not going to worry about using symmetry in this case, although it will be pretty helpful for calculating area under other types of polar curves that aren't this one. Okay, and I have an example where we will use symmetry later on in this video. But for now, let's focus on solving this definite integral to calculate the area of this region underneath this polar curve. All right, so the first thing that we can do to solve this definite integral is to square this quantity. Now, the quickest way to do that is to use a little trick. What we can do is square the first term, then add that to these two terms multiplied together, then multiplied by 2, and then add that to the last term squared. So if we do that, what we'll have is that this is equal to 1/2 times the integral from 0 to 2 pi of 3 squared, right? The first term squared, 3 squared is 9, plus these two terms multiplied together and then multiplied by 2. So 3 times sine theta is 3 sine theta times 2 will be 6 sine theta. So I have 6 sine theta, and then we'll add that to the last term squared, and sine theta squared will be sine squared theta. So we'll have plus sine squared theta, and then d theta. Okay, so now that we have squared this quantity, we have all three of its resulting terms, we can now work on integrating each of these terms individually. Now 9 and 6 times sine theta, those are pretty easy terms to integrate, right? 9 is a constant, and the integral of sine is a negative cosine. But sine squared theta is a little bit more difficult. That's going to require some extra steps. So what I'm going to do here is split up this integral into 3 separate integrals so that we can work on integrating each of these terms individually. So what we'll have is that this is equal to 1/2 times the integral from 0 to 2 pi of 9 times d theta plus 1/2 times the integral from 0 to 2 pi of 6 times sine theta d theta, and then we'll add that to 1/2 times the integral from 0 to 2 pi of sine squared theta d theta. All right, so we have an integral for each one of these terms, and you need to remember to have that 1/2 in front of each of those integrals. Okay, so now let's work on solving each of these integrals individually. With this first one, the integral of 9, which is a constant, will be equal to that constant times the variable of integration. In this case, we're integrating with respect to theta, right? That's why we have d theta. So the integral of 9 will be 9 times theta. So this is equal to 1/2 times 9 theta evaluated from 0 to 2 pi. Then we'll add this to 1/2 times the integral of 6 times sine theta. And the integral of sine theta is negative cosine theta. So we'll have negative 6 times cosine theta evaluated from 0 to 2 pi. And then with this last integral, we need to do a little bit more work before we can begin to actually integrate it, because there isn't a very nice integration rule for sine squared theta. This is where our skills for solving trigonometric integrals comes into play. And so if you're not familiar with solving trigonometric integrals, especially integrals where you have sine squared theta or cosine squared theta, be sure to check out my video on that topic as well. All right, but in the case where you have sine squared theta in your integral, the way you go about solving it is to rewrite sine squared theta using a trigonometric identity. Specifically, we're going to use the identity that sine squared theta is equal to 1/2 times 1 minus cosine of 2 theta. All right, so we're going to replace sine squared theta in this integral with this expression. So we will have plus 1/2 times the integral from 0 to 2 pi of 1/2 times 1 minus cosine of 2 theta d theta. All right, so now that we rewrote sine squared theta using that identity, we can now work on solving this integral. And so let's start by evaluating 9 theta at 2 pi and subtracting the evaluation at 0. So we'll have that this is equal to 1/2 times 9 times 2 pi minus 9 times 0. But 9 times 0 is 0, so we're just subtracting 0 here. So I'm just going to erase that. That doesn't affect our answer. So we're just going to have 1/2 times 9 times 2 pi. And then we'll add that to this expression. But before I evaluate cosine theta at 2 pi and 0, I'm going to pull this -6 out to the front. So we'll have -6 times positive 1/2, which will be -3. So I'm going to erase this plus sign, and we'll have minus 3 times cosine theta evaluated from 0 to 2 pi. All right, so we'll come back to that with our next step. But now let's continue on with this integral. We can pull this 1/2 to the outside and have 1/2 times 1/2, which is 1/4. So we'll have plus 1/4 times the integral from 0 to 2 pi of 1 minus cosine of 2 theta d theta. All right, now to further simplify this integral, or to actually solve it, we're going to need to split this up into 2 integrals. We'll have one integral for this term of 1 and another integral for this term of cosine of 2 theta. Because in order to integrate cosine of 2 theta, we're going to need to use u substitution. Cosine of 2 theta is a composite function, and so we need to set that inside function of 2 theta equal to u, and then we will be able to solve it using u substitution. So in our next step, we're going to split this integral up into 2 integrals, one for each term. Okay, but let's work on our next step here. We have 1/2 times 9 times 2 pi. This 2 and this 1/2 will cancel out, so we'll cross those out. We're just going to have 9 pi. All right, and then we will subtract 3 times cosine theta evaluated at 2 pi. Cosine of 2 pi is 1. So we'll have 1 minus cosine of 0, and cosine of 0 is also 1. So we have 1 minus 1, but 1 minus 1 is 0. So this is just 0 times 3, and so this whole term just becomes 0. All right, so I'm not going to bother to write that so we have more space for the rest of our work, and I'm just going to draw a line through this and say that it goes to 0. All right, now let's split this integral into 2 integrals and add that to 9 pi. So we'll have plus 1/4 times the integral from 0 to 2 pi of 1 d theta, and then because we have negative cosine of 2 theta, we're going to subtract the next integral of 1/4 times the integral from 0 to 2 pi of cosine of 2 theta d theta. Now, in order to solve this integral, like I said, we need to use u substitution. So let's start that process. We're going to set u equal to the inside function. So we're going to have u equals 2 theta, which means that du d theta, the derivative of u with respect to theta, will be equal to 2. All right, now to solve for du, we'll multiply both sides by d theta and have du is equal to 2 times d theta. Now, whatever du is equal to, we need to be able to find that within our integral, but I don't see 2 d theta, I just see d theta. So I'm going to divide both sides by 2, and then we'll have a term of du equal to something that we can find within our integral. So we'll have du divided by 2 is equal to d theta. All right, that's what we get when we divide both sides of the equation by 2. Okay, and so now we can work on our next step. We can solve this integral and rewrite this integral in terms of u. And so what we'll have is that this is equal to 9 pi plus 1/4 times the integral of 1. The integral of 1 will be theta. So we'll have theta evaluated from 0 to 2 pi, and then we'll add this to 1/4 times the integral from theta equals 0 to theta equals 2 pi of cosine u times du divided by 2. All right, I wrote the angles in this way, theta equals 2 pi and theta equals 0, because they're currently in terms of theta, while the rest of our integral is in terms of u. And so now's probably a good time to also change the bounds of integration to be in terms of u as well, so that we can just work in terms of u and not have to go back into terms of theta. All right, and so the way we can change our bounds of integration is to plug them into what we set u equal to. So for our lower bound, when theta equals 0, we'll have 0 times 2, which is 0, so u is also equal to 0 for that lower bound. So I'll replace theta equals 0 with u equals 0, and then for the upper bound, when theta equals 2 pi, we'll have 2 pi times 2, which is 4 pi, so the upper bound will now be u equals 4 pi. So I'll erase theta equals 2 pi, and we'll have u equals 4 pi. Okay, so now our integral is in terms of u, and it can stay in terms of u. So now for our next step, we will have that this is equal to 9 pi plus 1/4 times theta evaluated at 2 pi minus theta evaluated at 0. So we'll have 2 pi minus 0, which is just 2 pi. So we have 1/4 times 2 pi. All right, then we'll add this to this integral, and I'm going to pull this 1/2 out to the outside, so we'll have 1/4 times 1/2, which is 1/8, and that's going to be multiplied by the integral of cosine u du, and the integral of cosine is sine, so we will have sine of u evaluated from 0 to 4 pi. And then if we simplify further, this is equal to 9 pi plus 1/4 times 2 pi. 1/4 times 2 is 1/2, so we'll have 1/2 times pi, which is pi divided by 2. So we have 9 pi plus pi divided by 2 plus 1/8 times sine of u evaluated at 4 pi minus sine of u evaluated at 0. However, sine of 4 pi is 0 and sine of 0 is 0. So we have 0 minus 0, which is 0, and so this whole term will just become 0. We'll have 0 times 1/8, which is just 0. So we'll have plus 0 because this whole term just becomes 0. All right, so our final answer is just going to be 9 pi plus pi divided by 2, and we can combine that. 9 pi would be the same as 18 pi divided by 2, right? This would be equal to 18 pi divided by 2 plus pi divided by 2. 18 divided by 2 is 9, so this is the same as 9 pi. And now that we have a common denominator, 18 pi plus pi is 19 pi, so our final answer is that the area is equal to 19 pi divided by 2. That is the area of the region enclosed by this polar equation. Okay, let's take a look at another example. All right, so here's our next example. We want to find the area of the inner loop of r equals 1 plus 2 times cosine theta. All right, now the question itself kind of gives away what the shape of this polar equation is. It's asking us to find the area of an inner loop of a polar equation, which probably means that we're looking at a limacon with an inner loop. All right, and so let's check to see if that's true. This polar equation is in the form of a limacon. We have r equals some constant a plus or minus some constant b times cosine theta. In this case, a is 1 and b is 2. So a equals 1 and b equals 2. And so if we look at a divided by b, that's equal to 1 divided by 2, which is 1/2. And 1/2 is less than 1, which means that we have a limacon with an inner loop. All right, so that checks out. We know that we're working with a limacon whose graph will look something like this. All right, this is the general shape of the graph for a limacon with an inner loop when you're working with cosine. All right, so if we actually want to sketch a graph of this polar equation in our polar coordinate system, we need to make a note of a few points. First of all, the back end of our limacon, that's going to reach out to a radius of a plus b, and a plus b will be 1 plus 2, and that's equal to 3. So if each of these circles in this polar coordinate system represents a unit of 1 for the radius, then we'll count 1, 2, 3 right here. The back end of our limacon will be at this point right here. Now, for some more points, we know that the limacon is going to cross through the vertical axis at a value of a above and below the polar axis. And our value of a is 1. So our radius of 1 above the polar axis is right here. So we're going to cross through at this point, and we're going to cross through at this point, which is a value of 1 below the polar axis. All right, and then finally, we know that the inner loop is going to reach in to a radius of the absolute value of the difference between a and b. So a minus b, or 1 minus 2, is -1, and the absolute value of -1 is +1. So we're going to be at a radius value of +1 along the angle of 0 with that inner loop. So right here, where the radius is 1, we're also going to have a point. So if we connect our points, our limacon with an inner loop will look like this. We'll start at the back end, cross through this point, cross through the origin, make a loop, come back through the origin, through this point, and then close off our shape. And now we can work on finding the area that we want to calculate in this problem. Specifically, we want to find the area of the inner loop. So the area that we want to find is this small little area in there. We don't want to calculate the rest of this area, just that small little bit of area in the loop. And so how are we going to go about that? Well, we know we're going to need to use the following definite integral, that the area is equal to 1/2 times the integral from alpha to beta of r squared d theta. But what are going to be our two bounds of integration, right? How do we determine the two angles of theta that this area lies between? Well, the way that we can determine where that area is by noticing that this polar curve here, it's going to start at this point, right, at an angle of 0. If we were to plug that into our equation, cosine of 0 is 1. So you have 1 times 2, which is 2, plus 1, which is 3. So we have a radius of 3 at an angle of 0. So that takes us to 1, 2, 3 right here. That's our first point. And then if we were to trace our graph, it would go in this direction, cross through the origin, make a loop, and cross back through the origin and come back, right? That's how we drew this graph. And what I want you to notice about that tracing is that each time we crossed through the origin, that either started our loop or ended our loop, right? Let me trace it again. If we start here and come around, we cross through the origin, and now we're tracing our loop. And then when we cross back through the origin, we stop tracing the loop and we're tracing the rest of our limacon. So what we learn from this is that when the value of our radius is 0, when we are at the origin, that is when we are tracing the loop of our polar curve. So if we can determine what angles of theta correspond to each time the radius is 0, we can determine our bounds of integration. And the way we can do that is by setting our polar equation equal to 0, right? If we set r equal to 0 and solve for theta, that should give us two angles of theta for which this polar curve has a radius of 0, where the inner loop starts and where it stops. All right, so let's do that. We'll have 0 is equal to 1 plus 2 times cosine theta. We're just setting our polar equation equal to 0. Now let's solve for theta. If we subtract 1 from both sides of the equation, we'll have -1 is equal to +2 times cosine theta. And then if we divide both sides by 2, we'll have -1/2 is equal to cosine theta. And so now what we have to ask ourselves is, when is cosine theta equal to -1/2? Well, there's two angles where this happens. If you're working between 0 and 2 pi, those two angles will be theta equals 2 pi divided by 3 and 4 pi divided by 3. At each of these angles, cosine is equal to -1/2. Cosine of 2 pi divided by 3 is -1/2, and cosine of 4 pi divided by 3 is also -1/2. So what that tells us is that at these values of theta, for this polar curve, the radius is 0. So what that means is that the smaller angle, 2 pi divided by 3, that's the angle where our curve first hits the origin. Then the second angle, the bigger angle, 4 pi divided by 3, that's where our curve hits the origin the second time, after we make the full loop. So our lower bound will be 2 pi divided by 3, and our upper bound will be 4 pi divided by 3. Those are going to be the bounds of integration. Between those two values of theta, our polar curve is creating that loop, and so if we integrate between those two values of theta, we will calculate the area beneath that polar curve, which will be the area inside that inner loop. Okay, so let's set up our integral. We will have that the area is equal to 1/2 times the integral from 2 pi divided by 3 to 4 pi divided by 3 of r squared, and r is equal to 1 plus 2 times cosine theta, so we'll have 1 plus 2 times cosine theta squared times d theta. Okay, so just one more time, if we're looking at our polar graph here, we are integrating between the angle of 2 pi divided by 3 and 4 pi divided by 3. Okay, So by integrating between these two angles of theta, we are calculating the area of this inner loop. Okay, so now let's work on solving this integral in order to find the value of that area. All right, and so the first thing that I'm going to do to solve this integral is square this quantity. So we'll use a little trick to do that quickly. We'll square the first term and then add that to these two terms multiplied together, multiplied by 2, and then add that to the last term squared. So if we do that, the area will be equal to 1/2 times the integral from 2 pi divided by 3 to 4 pi divided by 3 of 1 squared, which is 1, right? We square the first term, and then we'll add that to 1 times 2 cosine theta. That will be 2 cosine theta, and then we need to multiply that by 2 to get 4 times cosine theta, and then we'll add that to the last term squared, and 2 times cosine theta squared will be 4 times cosine squared theta, right? 2 squared is 4, and cosine theta squared is cosine squared theta. And then don't forget d theta. All right, and so now we have 3 different terms that we need to integrate. Integrating 1 and 4 cosine theta is going to be pretty easy, but integrating 4 times cosine squared theta is going to be a little bit more difficult. So at this point, you could split up this integral into 3 parts like we did in the previous example, but I'm going to do it a little bit differently this time. I'm going to rewrite cosine squared theta using a trig identity first, and then we'll split up our integral after that. All right, because in order to integrate cosine squared theta, you're going to need to rewrite it using a trig identity. So I'm going to get that out of the way right now. We're going to use the identity that cosine squared theta is equal to 1/2 times 1 plus cosine of 2 theta. All right, so if we use this identity, we will have that our area is equal to 1/2 times the integral from 2 pi divided by 3 to 4 pi divided by 3 of 1 plus 4 times cosine theta plus 4 times 1/2 times 1 plus cosine of 2 theta d theta. All right, so we just replaced cosine squared theta with this identity 1/2 times 1 plus cosine of 2 theta. So now let's simplify this a little bit. 4 times 1/2 is 2. So the area is equal to 1/2 times the integral from 2 pi divided by 3 to 4 pi divided by 3 of 1 plus 4 times cosine theta plus 2 times 1 plus cosine of 2 theta. And that's still multiplied by d theta. All right, but now we can distribute this 2 through this quantity. We'll have 2 times 1 and 2 times cosine of 2 theta. I'm just going to do that right within this step. All right, so 2 times 1 is 2, and 2 times cosine of 2 theta is 2 times cosine of 2 theta. So what we'll have is 2 plus 2 times cosine of 2 theta. All right, so now what we can do is combine our like terms. This is why I waited to split up the integral. We can actually add 1 and 2 to get 3. So this will be equal to 1/2 times the integral from 2 pi divided by 3 to 4 pi divided by 3 of 3 plus 4 times cosine theta plus 2 times cosine of 2 theta d theta. All right, so now at this point, it would be a good idea to split up this integral into 3 integrals, 1 for each of these terms. 3 and 4 times cosine theta are pretty easy to integrate, but 2 times cosine of 2 theta is going to involve u substitution. It's a pretty easy u substitution, but it will require more steps than integrating these 2 terms. All right, so if we split this up, this will be equal to 1/2 times the integral from 2 pi divided by 3 to 4 pi divided by 3 of 3 d theta plus 1/2 times the integral from 2 pi divided by 3 to 4 pi divided by 3 of 4 times cosine theta d theta, and then we'll have plus 1/2 times the integral from 2 pi divided by 3 to 4 pi divided by 3 of 2 times cosine of 2 theta d theta. All right, so now we can work on integrating each of these integrals separately. And so if we start with our first integral, the integral of 3, that's a constant. That's just going to be 3 times theta. So this is equal to 1/2 times 3 theta, evaluated from 2 pi divided by 3 to 4 pi divided by 3. Then we'll add that to this integral. If we pull this 4 to the outside before integrating, 4 times 1/2 is 2. So we'll have 2 times the integral of cosine, which is sine. So we'll have sine theta evaluated from 2 pi divided by 3 to 4 pi divided by 3. All right, and then for this last integral, if we pull this 2 to the outside, we'll have 2 times 1/2, which is just 1. So 2 and 1/2 actually cancel each other out. So we'll just have plus the integral from theta equals 2 pi divided by 3 to theta equals 4 pi divided by 3. And I'm going to work on using u substitution here. That's why I wrote these bounds of integration in this way. We'll work on writing those in terms of u in just a second, but let's set u equal to this inside function of cosine of 2 theta. We'll have u is equal to 2 theta, which means that du d theta is equal to 2. The derivative of u with respect to theta is 2. If we multiply both sides by d theta, we'll have du is equal to 2 d theta. But because this 2 and this 1/2 canceled out, we don't have 2 d theta in our integral, we just have d theta. So if I divide both sides of this equation by 2, we'll have du divided by 2 is equal to d theta, and now we have a term of du that can replace d theta in our integral. Okay? So if we rewrite our integral in terms of u, we'll have cosine of u times du divided by 2. Now for the bounds of integration, we'll plug these values of theta into what we set u equal to change them from being in terms of theta to being in terms of u so that we can just continue to work in terms of u and we don't have to go back into terms of theta. All right, so if we plug in this lower bound, we'll have 2 pi divided by 3 times 2, right? 2 times theta. So the new lower bound will be u is equal to 4 pi divided by 3. So I'll just erase this and we'll have u is equal to 4 pi divided by 3. And then for the upper bound, we're just going to be multiplying this value of theta by 2 as well. So 4 pi divided by 3 times 2 will be 8 pi divided by 3. All right, so our new upper bound will be u equals 8 pi divided by 3. Okay, so now we don't need this u substitution work anymore. Our integral is entirely in terms of u. Now if we work on simplifying, we'll start with this term. I'm going to pull 3 to the outside. So this is going to be equal to 3/2 times theta evaluated from 2 pi divided by 3 to 4 pi divided by 3. And then we have plus 2 times sine of 4 pi divided by 3 minus sine of 2 pi divided by 3. Sine of 4 pi divided by 3 is the negative square root of 3 divided by 2. And then we're subtracting sine of 2 pi divided by 3, which is the positive square root of 3 divided by 2. All right, and so then we'll add this to this integral, which if we pull this 1/2 to the outside, we'll have 1/2 times the integral of cosine u, which will be sine u. The integral of cosine is sine, and that will be evaluated from 4 pi divided by 3 to 8 pi divided by 3. All right, now if we simplify further, this will be equal to 3/2 times 4 pi divided by 3 minus 2 pi divided by 3. Right, we just evaluated theta at 4 pi divided by 3 and subtracted the evaluation at 2 pi divided by 3. Now for this term, we have the negative square root of 3 divided by 2 minus the square root of 3 divided by 2. If we combine them, we will have plus 2 times negative 2 square roots of 3 divided by 2. All right, we have 2 of those fractions, so we have 2 times the negative square root of 3 divided by 2. Then we'll have plus 1/2 times sine evaluated at 8 pi divided by 3. That's equal to the square root of 3 divided by 2. And then we will subtract sine evaluated at 4 pi divided by 3. And sine of 4 pi divided by 3 is the negative square root of 3 divided by 2. Okay, so now if we simplify, let's start with this first term. 4 pi divided by 3 minus 2 pi divided by 3, that's going to be 2 pi divided by 3. So this is equal to 3/2 times 2 pi divided by 3. And then we'll add this to this term. But notice that negative 2 divided by 2 will be negative 1. These two 2's will cancel out. So we have 2 times the negative square root of 3. So actually, instead of adding this term, we will have minus 2 square roots of 3. And then we'll add this to 1/2 times this quantity, where we have the square root of 3 divided by 2 minus the negative square root of 3 divided by 2. These two negatives will cancel out, so we'll have the square root of 3 divided by 2 plus the square root of 3 divided by 2. So that will give us 2 square roots of 3 divided by 2. All right, and then to simplify further, let's go back to our first term here. Notice that these two 3's are going to cancel out, and these two 2's are going to cancel out, right? 3 divided by 3 is 1, and 2 divided by 2 is 1. So we can cross all of those values out, and we're just going to be left with pi. So this is equal to pi minus 2 square roots of 3, and then we have plus 1/2 times 2 square roots of 3 divided by 2, but those 2's are going to cancel out. 2 divided by 2 is 1, so we have 1/2 times the square root of 3. All right, and then finally, negative 2 square roots of 3 and positive 1/2 square roots of 3. If we add those two terms together, negative 2 plus 1/2 is negative 3/2. So this is equal to pi minus 3/2 times the square root of 3, which you could rewrite to be pi minus 3 square roots of 3 divided by 2. And that is the area within the inner loop of this polar curve represented by this polar equation. Okay, let's take a look at one more example for this video. All right, so here's our last example. We want to find the area of the region enclosed by r squared equals 4 times cosine of 2 theta. Now, if you're familiar with your different types of polar equations and your special types of polar graphs, you might recognize this polar equation right here to be the polar equation of a lemniscate. All right, specifically, since we're working with cosine, not sine, the graph of the lemniscate will look something like this. It looks like an infinity symbol. All right, the general form of a lemniscate dealing with cosine is r squared is equal to a squared times cosine of 2 theta. All right, so in this case, a squared is the same as 4. So a squared is equal to 4, which means a will be equal to 2. Okay, a is always going to be a positive value, which is why we say that a is equal to 2 rather than negative 2, because the square root of 4 would also be negative 2. Okay, if you're going to have a negative sign in front of this constant, it would be negative a squared. And so no matter what, that value of a would be positive. All right, so if this was negative 4, we would still set 4 equal to a squared, and a would still be equal to 2. Okay, but anyway, this value of a tells us how far from the origin, or the value of the radius, to which each one of these loops for this infinity sign reaches out to. All right, this is actually going to be pretty simple to graph in our polar coordinate system here, because if we say that the fourth circle here is a radius of 2, right, if this is a radius of 2 and the second circle is a radius of 1, and that's true in both directions, then we can very quickly draw our lemniscate to look like this. All right, that's just a sketch of the graph. A lemniscate for cosine is just this infinity symbol that crosses through the origin and reaches out to a radius of a, which in this case is 2. Okay, so this is our graph, and so what we want to do is calculate the area enclosed by that graph, or enclosed by that polar curve. And so that area will be the area in both of these loops. All right, now what's important to realize here is that there's a lot of symmetry going on with this polar curve. And we're going to take advantage of that when we set up our definite integral. Okay, because this lemniscate, this polar graph, is symmetric about the vertical axis and the horizontal axis. It's the same on the left as it is on the right, and it's the same on the top as it is on the bottom. And so we can really take advantage of symmetry here. All we have to do is calculate the area of 1/2 of one loop and then multiply it by 4, right? So if we calculate the area of just this 1/2 of this loop, multiplying it by 2 would account for this whole loop, but then multiplying it by 2 again, or just multiplying this half by 4, would account for 1, 2, 3, 4, all 4 of those halves for the entire area. So we can make this into a pretty nice integral to solve. Remember that we will use the definite integral, that the area is equal to 1/2 times the integral from alpha to beta of r squared times d theta. We know that r squared is equal to 4 times cosine of 2 theta. That's a pretty easy substitution. But determining alpha and beta, our angles of theta, is going to be the tricky part. But it's actually not going to be too bad, because all we have to do is determine what angles of theta take us from this part of the curve to this part of the curve. We just have to calculate the area beneath the curve from here to here, 1/4 of our curve. All right, and so how do we determine that? Well, first of all, note that this curve is going to start at the angle of 0, which will be this point right here. If you plug 0 in for theta into this equation, cosine of 2 times 0 will be cosine of 0, and cosine of 0 is 1, so you have 1 times 4, which is 4, and then you have r squared is equal to 4, and if you take the square root of both sides, that gives you 2, and so you know when theta equals 0, that the radius will be 2. That takes you to this point right here, a radius of 2 and an angle of 0. So we're starting here, and then if we were to trace the curve, it would be drawn in this way, as we would work with bigger and bigger angles. So we know that the lower bound will be 0. We're starting here. We just have to determine what angle corresponds to this point right here when the curve reaches the origin. Now you might be tempted to say that that's pi divided by 2, but that's not actually the case, so don't make that assumption. Instead, what you want to do is determine where the radius is 0 for this polar equation. All right, so if we set r equal to 0 in this polar equation and then solve for theta, the smallest value of theta that we find, the smallest angle, that will give us that first angle where the radius will be 0, where the curve hits the origin for the first time. So let's do that. If we let r equal 0, we'll have 0 squared is equal to 4 times cosine of 2 theta, and 0 squared is just 0, so we don't even need to write 0 squared. And then to solve for theta, we can divide both sides by 4. 0 divided by 4 is 0, so we have 0 is equal to cosine of 2 theta. And now to solve for theta, we just have to determine when is cosine equal to 0 and set those angles equal to 2 theta to then solve for theta. In this case, we know that cosine is equal to 0 at pi divided by 2 and 3 pi divided by 2. So if we set 2 theta equal to pi divided by 2 and 2 theta equal to 3 pi divided by 2, we will find the values of theta for this equation where the radius is 0. Okay, once again, we know that cosine of pi divided by 2 is equal to 0 and cosine of 3 pi divided by 2 is 0. So we're setting this angle equal to those angles to figure out what value of theta would give us that angle for cosine such that it's equal to 0. All right, so if we divide both sides of these equations by 2 to solve for theta, we'll find that theta is equal to pi divided by 4 and theta is equal to 3 pi divided by 4. All right, dividing by 2 is the same as multiplying by 1/2. And so out of these two angles, pi divided by 4 is the smallest angle, so that means when we are tracing our curve, if we're starting at an angle of 0, when we first hit the origin, where the radius is 0, that's an angle of pi divided by 4. And then when we wrap around and come back in, when we hit the origin the second time, that's an angle of 3 pi divided by 4. All right, so we're not worried about that angle. We want to use this angle. At the angle of pi divided by 4, that's this angle right here, that's where our curve hits the origin for the first time, so that means between the angles of 0 and pi divided by 4, that's where this curve lies, which is where this area beneath this curve is located. So if we calculate this area beneath this curve, which remember, that's only going to be 1/4 of the area, and then multiply that area by 4, we will have the area of the entire region. All right, so now let's set up our integral. The area will be equal to 4 times 1/2 times the integral from 0 to pi divided by 4 of r squared, which is 4 times cosine of 2 theta. So we have 4 times cosine of 2 theta, and then d theta. All right, so our bounds of integration are from 0 to pi divided by 4. Those are the two angles of theta that this quarter of our area lies between. And then because it's only a quarter of the area, we're multiplying the area by 4. That's why we have 4 times this integral. Okay, and so now we have a pretty simple integral to solve. Cosine of 2 theta can be integrated using u substitution. But first, let's simplify this a little bit by pulling out this constant of 4 to the outside and multiplying our constants together. 4 times 1/2 is 2, and 2 times 4 is 8. So this is equal to 8 times the integral from 0 to pi divided by 4 of cosine of 2 theta d theta. Okay, so to solve this integral, we need to use u substitution because cosine of 2 theta is a composite function. We're going to set u equal to that inside function. So we'll have u is equal to 2 theta, which means that du d theta is equal to 2. This is like the third time that we've done u substitution for 2 theta, so hopefully you know where we're going by this point. If we multiply both sides by d theta, we'll have du is equal to 2 times d theta, and whatever du is equal to needs to be within our integral, but I don't see 2d theta, I just see d theta, so we need to divide both sides by 2, and we'll have du divided by 2 is equal to d theta. So we can replace d theta with du divided by 2. All right, so the area is equal to 8 times the integral, and I'm going to rewrite our bounds of integration in terms of u in just a second. So I'm going to leave those blank for now. I'll come back to that. And then inside the integral, we'll have cosine of u times du divided by 2. All right, now for the bounds of integration, let's plug these values of theta into what u is equal to. When theta equals 0, we have 2 times 0, so u is equal to 0. So the lower bound in terms of u will be 0. And then for the upper bound, when theta is pi divided by 4, we'll plug that in for theta. 2 times pi divided by 4 is pi divided by 2. So the upper bound in terms of u will be pi divided by 2. All right, so this integral right here is in terms of theta, and this integral right here is in terms of u. All right, so this is where the u sub took place. Now, if we pull 1/2 to the outside, 1/2 times 8 is 4, so this is equal to 4, and then that's multiplied by the integral of cosine, which is just sine. So we'll have 4 times the integral of sine u evaluated from 0 to pi divided by 2. All right, now to simplify, we can evaluate sine at pi divided by 2 and subtract the evaluation of sine at 0. And so this will be equal to 4 times sine of pi divided by 2 minus sine of 0. Sine of pi divided by 2 is 1, and sine of 0 is 0. So this is equal to 4 times 1 minus 0, which is just equal to 4 times 1, which is 4. So weirdly enough, the area within this polar curve for this lemniscate is a really nice value of 4. You might find that hard to believe, but that is the area enclosed by this polar equation. Okay, and so with that, this was the last example for this video. So if you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.